System of nuclei with spin 1. Consider a nucleus having spin 1, spin angular momentum h bar. Its component mu of magnetic moment along a given direction can then have three possible values, namely plus mu 0, 0 and minus mu 0. Suppose that the nucleus is not spherically symmetrical but is ellipsoidal in shape. As a result, it tends to preferentially be oriented so that its major axis is parallel to a given direction in the crystalline solid in which the nucleus is located. There is thus a probability P that mu is equal to mu 0, a probability P that mu is equal to minus mu 0, and the probability that mu is equal to 0 is then equal to 1 minus 2p. Calculate mu bar, mu square bar, the variance of mu. Suppose that the solid under consideration contains capital N such nuclei which interact with each other to a negligible extent. Let M denote the total component of the magnetic moment along the specified direction of all these nuclei. Calculate M bar and standard deviation delta M tilde in terms of N, P, and mu 0. So let's start with part A. Now we see that the possible mu values are mu 0, 0, and minus mu 0. So we have the possible values mu 0 with probability P, 0 with probability 1 minus 2p, and then we have the value minus mu 0 with probability p. So the mean value of mu is by definition sum over r, pr mu r. So here r goes from 1 to 3. So we have p1 mu 1, p2 mu 2, p3 mu 3, which is p1 is p, mu 1 is mu 0, p2 is 1 minus 2p, mu 2 is 0, and the third one p times minus mu 0. So you can see here the second term is 0, and the first and the third term will give me for mu bar mu 0 p minus mu 0 p. Therefore, I calculate the mu bar to be 0. Now I want to calculate the average value of mu square. So again, let's use the definition of mu square average. It is sum over r probabilities and corresponding mu r square values. So mu square values I have are mu 0 square, 0 and mu 0 square with probabilities p, 1 minus 2p and p. So this is going to be mu 0 square with probability p, 0 with probability 1 minus 2p, and again minus mu 0 squared with probability p. So I find that mu square average value should be 2 mu 0 square p. So that's basically it for part A. So let's look at part B. Part B asks me the variance of mu. So it is delta mu, deviation from the mean, squared average value. That's the variance or dispersion of mu. So this is, although we have done it in the previous problem, let me do it one more time. The deviation from the mean, mu minus mu bar, square average value. So this is mu square minus 2 mu bar plus mu bar square average value. That is mu square bar minus 2 mu bar squared plus mu bar squared. So it is mu squared bar minus mu bar squared. Okay, so do I know these? From part A, I know what mu bar is, and I know what mu square bar is. So for the variance of mu, I can write mu square bar, that is 2 mu 0 square p, minus mu bar was 0 minus 0 squared. So I find that the variance of mu, delta mu square bar, should be 2 mu 0 square p. So that is the answer to part B. Now in part C, we're talking about the total total component of magnetic moment along the given direction, where I have either plus mu 0 or the component minus mu 0 on the same axis. So I'm going to calculate the average value of m. So let's think about what m is. So m is, by definition, the sum I equals 1 to capital N mu I. Basically, I'm looking at the magnetic moment of each component, each nucleus, and adding them up to get the total magnetic component, a magnetic moment component in that direction. So if I want to calculate m bar, this would be equal to sum I equals 1 to n mu I bar. Since they are not interacting with each other, this would be equal to I equals 1 to n mu I bar, and mu I bar is the same for each nucleus, it's mu bar. So therefore I find the mean value of m to be capital N times mu bar. So mean value of capital M is 0, because it's capital N times mu bar. Now I'm going to talk about the standard deviation. So let me remember what standard deviation was. Standard deviation of m is defined as root mean square root of deviation from the mean square average value. So basically it is square root of m square bar minus m bar square root. Okay, so I know what m bar square is, but I don't know what m square bar is. So let me think about m square. M square will be the product I equals 1 to n, capital N mu I, multiplied with j equals 1 to n mu j. So summation over j. So if I open this up, I will find that capital M square will have terms where I is equal to j. So this is going to give me I equals 1 to capital N mu I squared. Then I will have terms for I and j. They go from 1 to n, but I is not equal to j. Let me basically clarify that I have two summations, summation over I and summation over j, and I is not equal to j. So that means that I have the product mu I mu j. This is cross terms, but I have the condition that I is not equal to j. So if I goes from 1 to n, then the number of terms for the j summation will be capital N minus 1, because I have the condition whenever I choose a value for I, that value is forbidden in the summation of j. So this is going to give me, when I take the average value of this is going to give me sum I equals 1 to n mu square average value plus capital N times capital N minus 1 mu bar times, or let's do it one more step here. This is going to give me I equals 1 to n and sum over j for I is not equal to j, mu I mu j bar. So because they are statistically independent, I can write it this way. So this will give me capital N terms in the first one, so capital N mu square bar, and then I have n terms from I summation and n minus 1 terms, because I is not equal to j, for the j summation times mu bar squared. So for m square bar, basically, since mu bar was 0, so this term is going to disappear, and I will end up with capital N times mu square bar. So I find that m square bar is equal to, because mu square bar was 2 mu 0 square p, 2n mu 0 square p. Now going back to the standard deviation in m, so standard deviation of m is m square bar, which is 2n mu 0 square p minus m bar squared, 0 squared to the 1/2. So I find that the standard deviation of the total magnetic moment will be mu 0 times square root 2n p. Okay, so let's go over what we have done here once again. We have a nucleus that has spin 1, so it can have plus mu 0, 0 or minus mu 0 magnetic moments in 3 possible directions, magnetic moment components. And plus mu 0 and minus mu 0 values have probability p. 0 has value 1, probability 1 minus 2p. So the average value of mu is going over all possible mu values multiplied with their probabilities and then summed up. So that gives us for mu bar 0. And for mu square bar, it's a function of mu basically. We have the average value of a function of mu is by definition sum over r pr f of mu r. So for mu square, where the function is mu square, we have mu 0 square p plus 0 1 minus 2p plus minus mu 0 square p. So that gives us 2 mu 0 square p. For the variance of mu, we have to calculate mu square bar minus mu bar squared. Well, mu square bar, we know 2 mu 0 square p. Mu bar was 0, so the answer is 2 mu 0 square p. For the total magnetic moment component, m, capital M, it's the sum over all magnetic moment components from each nucleus. So we have capital N nuclei, therefore the sum is I equals 1 to capital N mu I summation. However, when we take the average value, the average value of mu I is the same for each nucleus. They're statistically independent, so I have capital M bar is n capital N times mu bar, which is 0. For the standard deviation, I have to calculate, similar to part B, m square bar minus m bar square square root. Root means square. So I already know m bar is 0, so all I have to do is calculate m square bar. So what is m square? It's the product I equals 1 to n summation mu I and j equals 1 to n mu j. And that's going to give me terms where I is equal to j. So that is mu1 squared plus mu2 squared plus mu3 squared, etc. And then I will have capital N terms and capital N minus 1 terms for the I and j summations, because I is not equal to j. So this is going to give me capital N times capital N minus 1 mu bar squared. Well, this term mu I times mu j average value is mu I bar times mu j bar, because they're statistically independent. So we have capital N minus 1 mu bar squared. So that is going to give me 0. Therefore, we find that m square bar is 2 capital N mu 0 square p. We just need to take the square root to find the standard deviation, which is mu 0 square root 2n